Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the Longifolene, the fourth way of synthesizing Longifolene in the laboratory by using as a different method, and there are the different starting material, the precursors are used as a different, and there we are getting as a some of the intermediate, some of the interesting intermediate or the key intermediate is obtained, and main thing is here for the purpose behind synthesis of Longifolene is it is a tricyclic, it contains as a 15 carbon atom, it is a hydrocarbon and it has a 4 that Longifolene has 4 chiral center and it is a natural product as well as it is a tricyclic compound. Only one of the functional group present over there is a carbon-carbon double bond, means olefinic, and it is a hydrocarbon, and therefore to make carbon-carbon bond formation it is a challenge before the organic chemist, and that methodology we are learning here by maintaining the stereochemistry while synthesizing this compound is very essential, and we should ensure that all these steps are very crucial while synthesizing this compound, and up till now we have seen as a fourth way. Now today we are going to discuss about the fifth way of synthesizing, a fifth way. There is a fifth way of synthesizing Longifolene, because we are discussing the synthesis of Longifolene. So scheme 13.28, here is a scheme 13.28, Longifolene synthesis. Longifolene synthesis, and this synthesis is described by the scientist, the name of that scientist W.S. Johnson and co-workers W. Johnson and co-workers, they have described here the Longifolene synthesis by taking as a starting material is a different. So let's what they have taken as a starting material and how they have synthesized the Longifolene. And we know that the structure of the Longifolene, so that the target molecule we are synthesizing. So this is our target molecule. Here is a CH2. There are 2 methyl group and 1 methyl group is here. So this is our target molecule. This is the structure of the Longifolene, and the numbering system also you know that numbers start from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, then 13, 14, and last one olefinic is a 15. So this is the numbering. There are 15 carbon atoms are present, and one is a olefinic is a functional group present, and it is a tricyclic. Look at, there are one 6-member ring, another one is 1, 2, 3, 4, 5, 6, 7, 8-member ring, and one is a 5-member ring. So there are the 3 rings, tricyclic. It is a hydrocarbon. There are 4 chiral center, that also we know that at carbon number 1 chiral center, at 2 is a chiral center, then 7 is a chiral center, and the 10. So there are the 4 chiral center which exist in a Longifolene. It is a natural product, and this is the favor. This Longifolene we are synthesizing. There are 9 different ways or the method by starting as a different starting material and the different reagent using, and finally we can achieve the target molecule which is a Longifolene in the laboratory. So let's see what are the starting material taken for the Longifolene. Ultimate or the final goal to achieve the Longifolene by taking as a different starting material and the reagent. Let's see over here the starting material, in this case taking as this one CS3, C triple bond C, then CH2, CH2, CH2 and iodine. This is the starting material. If you see the IUPAC, as we know that IUPAC means International Union of Pure and Applied Chemistry, there are the certain rule. According to that rule you can able to find out its IUPAC name. So there one halide is there, and here carbon carbon triple bond is there. So halide, it can be treated just like as a branching alkyl halides. Suppose as a methyl groups are there. So but the functional group present over here, carbon carbon triple bond as well as halide also. From here to start as a numbering, so you can give the numbering from this side. Suppose as a 1, 2, 3, 4, 5 and 6. At 4 position there will be a what we can call it as a triple bonds are present. So you can give 1 iodo, 1 iodo, 1 iodo, Higgs, 4 what we can call it as 6 carbon atom are in the straight chain. At 4 position there will have carbon carbon triple by Y and E, or we can call it as a 1 iodo, 4 hexine. Either you give this or that way, both are the what we can call it as a way to give the IUPAC name of this compound. This is our target this is our starting material or the precursor taken for the synthesis of Longifolene, the 4th way or the 4th method. Now here first one is a reagent. What are the A reagent added over here? First one, here is added tertiary butyl lithium. Tertiary butyl lithium, and second reagent is added over here is a cuprous iodide, CuI. That the reagent, and by using as a these reagent we may get as a Gilman type of the product over here. So here you are going to get CS3, C triple bond C, then CH2, CH2, another CH2 bracket twice, and you can write here is a Cu. This is a cuprous type of the compounds are formed here, and these reagent further treated with this the reagent which we obtain over here. So now this cuprous generally treated with the compound like this. Here is a 5-membered C double bond O, double bond, then C here CS3 twice you can write over here. So this is the compound is alpha beta unsaturated carbonyl group is alpha beta unsaturated. Now this reagent and this adding together this one, what do you get over here? And now after adding this, we are going to get, and then there will be a B added, that is a CH3COCl3, that is acetyl chloride is added. Now here what is happening, after adding all these things, what you are going to get? So you are going to get here the compound will be this one. So 5-membered ring after adding as a B reagent. This is A reagent, after adding A reagent we got this, and then adding as a this with this and CH3COCl, that B, and we are going to get the product is here OAC double bond, then here will be CH3, then there is a 3 CH2, C triple bond C and the CH3. This is a product which we are getting over here after the addition of this. Now if you see over here, for the mechanism point of view, how do we get this compound? So let's try over here. Now we know that here will be a negative charge. So for mechanism point of view, I am going to show here this. Okay, let me draw the mechanism point of view over here like this. CH3, C triple bond C, then CH2, then CH2, this one, then Cu. Now this is negative charge, here should be as a positive, and now this nucleophile is going to attack on this. Let us see here, this is a alpha beta unsaturated compound. There I am writing over here CH3 and this CH3, 2 methyl group. For mechanism point of view I am writing over here, and another one, so C double bond O Cl and this methyl group. Now this negative is going to attack because this is a just like as a Gilman's reagent, it prefer to add 1,4 position. This is a alpha and beta position. So 1,4 position. So this is a 1, 2, 3 and 4 position. Addition is going to occur here, and this double bond shifted from here to here, and this double bond is going to attack over there, this carbonyl group, and then there is a departure of Cl. So now if you do all these things, you will get this type of the product. Look at here, double bond here, and OAC means this acetyl group is there, and rest of the thing methyl group, all these CH3, C triple bond C, CH2. So this is the product which we got over here. This is a mechanism point of view I am shown over here. And after that, this after getting as a this, let me show another. Here I am adding the reagent C here. Is A, the reagent B, and now is a C. What are the C reagents added over here? First one, methyl lithium. First one is a methyl lithium. This is a strong base. Second one, addition of Br2, and third one, what we are adding, that is again Ar CO2 minus, that is a acetate ion, that is a weak base is used over here. After adding all these reagents, what do you get? you are going to get the product form will be this one. Now there will be a this C double bond O alpha beta unsaturated, then this CS3, this CS3, another one CH2, 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 C triple bond C and CS3. This is the compound which we got after the treatment of these three reagents on this particular, and we got as a this. Now how do you get here alpha beta unsaturated compound in a 5-membered ring? Let's see the mechanism point of view over here. So let me clean this first, and I am trying to show this one. Now here methyl lithium is a strong base. See over here, this is a compound I am writing over here. This is the 5-membered ring, right? Then O, C double bond O, CS3, double bond here, then C. For sake of convenience, I am taking here this whole part. This part I am considering as a R. Means R is equal to, you can take here, this I am taking as a R over here, so that we can show the clarity in the mechanism, and that's the purpose of this group. This group R is equal to C here CS3, CS3, CH2, CH2, 3 CH2 and C triple bond C and CS. This is the R group I have taken over here as a mechanism point of view. Now here we know that CS3 Li, we know that lithium metal are always carries positive charge, and this nucleophile is going to attack on maybe as on carbonyl group, retain. So is double bond here, and here Br plus delta charge minus delta charge. This double bond is going to attack over there, and you will get this type of the situation. So here you can get here C double bond O, then now here R, this double, now here is a Br. Now this the proton which may abstract by this AR like this, and double bond are formed over there, and finally you are going to get the product this one. That's the probable mechanism I have shown over here. This is a possibility we get this type of the compound. Now let me clean this once again, and now what do you get over here? On this, here is a C, here is a D point, one lithium aluminum hydride, and the second one, that is acidic H plus. Here you might be thinking there are carbonyl group is going to reduce, but interestingly here the tricyclic compounds are formed. This is a very interesting tricyclic compound is formed when there is addition of most of the chemists thinking here the lithium aluminum hydride is a reducing reagent, it can reduce as a carbonyl group into as a alcohol, and there the H plus acidic condition, there is a tricyclic compound. This is a very interestingly formed over there, and we are going to get the formation of the product is this one. This is the product which we are going to get over here, double bond here methyl group, these two methyl group, they are already over there, and here we are getting as a hydroxy group. So this is the product which we are getting after the treatment of D, lithium aluminum hydride. Then the acid treatment is preferentially gives you this type of the photolysis reaction is occur, and it form as a directly as a what we can call it as a this kind of the tricyclic compound is formed, and after that this compound further treated with DE reagent when we are adding number 1 zinc bromide ZnBr2, and second will be the NaBH3BH3Cn. It is one of the reducing reagent which selectively reduce the carbon-carbon by using as this reagent, particularly ZnBr2 and NaBH3, it selectively or reductively removed as a hydroxyl group from the target molecule. So that is a specialty. This is also as a very interesting. When you are adding as these reagent, particularly it reductively reduce the hydroxyl group from the bridgehead, and finally we are going to get the product. Here is this one, the product which we are going to get here is this is the product which we are going to get over here, this one CS3 and 2 methyl group. Only changes is there, this hydroxyl group is reductively removed, selectively removed by using as this reagent, that is zinc bromide and the sodium borohydride cyanide. So that is sodium cyanoborohydrate. So that is the name of that compound. And after that, when this compound further treated with the reagent, here is a F reagent, and F reagent first one will be the acid treatment over here, acid treatment, so that there is a tertiary carbocation is formed, and then second reagent RuO4 ruthenium oxide and IO4 minus, which selectively remove the methyl group from there, and the third reagent which I am adding here LiNR2, that is a LDA type of the reagent. Then methyl iodide, minus and positive charge over there. So selectively we can introduce, but while adding all these reagent, H plus here positive charge is formed, this reductively remove that methyl group, then lithium LDA type of the strong will abstract the proton from here, form as a carbanion, and that is going to attack on that methyl group. So by adding these reagents selectively, they have removed this methyl group and introduce methyl group at bridgehead. So that is the, and as well as here is the introduction of carbonyl group and methyl group by adding this, and we are going to get the product over here will be this one, is structure. Here is a carbonyl group, here is a methyl group introduced, and this 2-methyl group is already over there. And once you got this compound, and as we know that by using the Wittig reagent we can get the final compound will be the Longifolene, or they have used, instead of Wittig, they have used as a different approach here to get as a Longifolene over here. Number one they have added here is a CS3Li, lithium, methyl lithium, or lithium methyl. Then second will be the SOCl2 thionyl chloride in presence of the pyridine, and they are selectively and they got as a Longifolene, which is our target molecule. And as we know that the structure of Longifolene will be the same. So in addition to the key cationic cyclization in step D, which we have seen over here, cationic interesting transformation were carried out in step E, where bridgehead tertiary alcohol was reductively removed, and in step F were a methylene group which was eventually reintroduced had to be removed. The endocyclic double bond, which is strained because of its bridgehead location, was isomerized to the exocyclic position and then cleaved with ruthenium oxide IO4 minus. The enolate of the ketone was then used to introduce the C12 methyl group in step F3 and F4 methyl group. The synthesis in scheme 13.29 also uses a remarkable simple starting material to achieve the construction of the tricyclic skeleton. A partial retrosynthesis is outlined below in the further case. I think in this way we have learned, we have discussed the synthesis of Longifolene here, and 6 scheme that we will discuss in our next lecture. Let us stop today here. Remaining we will see in the next lecture. Till then, have a nice day. Thank you.